Hello geologists. In this video I'm going to review how to make a topographic profile or topographic cross-section from a topographic map. And we're going to be constructing that profile in the space beneath here. Sometimes you can construct it on a separate piece of paper. That works as well. So for doing this you're going to need a good calculator, a nice ruler protractor. I prefer these Westcott see-through W8s, which are divided into tenths of an inch, and a nice pencil. So you're going to need all of that stuff. So the first thing we do is we look at our map to interpret it. And notice we've got a scale bar, a contour interval of 10 feet, and one contour line that is labeled. And we have a stream here. So there is our key, right? Just when we look at this, if we didn't have the stream, we wouldn't be sure which way is going uphill and which way is going downhill. But as soon as we see a stream in those stream valleys, by the rule of V's, where a contour line crosses the stream, it always makes a V which points in the upstream direction. So that means that the lowest elevation on our map is going to be down here in the southeast corner, and the highest elevation then is going to be going away from the stream, and we see a hill over here. So that's how we know that this is a hill and not a valley, because we've got already the stream here. So next we need to take a look at what our maximum elevation is and our minimum elevation. Our minimum elevation is always going to be along the stream. So if this is 500, it's going to go down to 490, 480, 470, somewhere between 470 and 460 feet. So the lowest elevation here is going to be just above 460 feet. And the highest elevation here is going to be just above 510 feet. We're going to create a topographic profile along the trace of this line A to A prime, and we're going to project it down into this space here. So now I did a little work ahead of time which is going to save us some trouble. So on this map I've labeled every single contour line. That's going to help us. And now we need to figure out our scale. We need to know our horizontal scale, and from that we're going to make our vertical scale. So how are we going to figure out our horizontal scale? The easiest thing to do, if you have any 2 points on a map, you can measure the distance between those 2 points. And if you know the real world distance, you can figure out what that ratio is. So on the scale bar, we have 2 points with a real world distance of 100 feet in between those two. So I can measure the distance between those two, and I'm going to call it 0.92 inches is going to be equivalent to 100 feet. If I measure that really carefully, I'm going to call that 0.92 inches. So that means our horizontal scale is 0.92 inches for 100 feet. But what we really want to do is excuse me, grab my other notes here. What we really want to do is figure out what the what 0.92 inches is in the real world. So first of all, we need to convert those two. We've got feet and we've got inches we're going to measure on the map for convenience, because we can't very well measure feet on the map. So we want to take 100 feet and convert that into inches. So we're going to do our calculations over here. 100 feet, and we always know that there are 12 inches per foot, so feet cancel out, and we're left with 1,200 inches. Could have done that calculation in our head. In other words, this distance here on the scale bar is 100 feet or 1,200 inches. So now we can set up our ratio. We measured this distance here at 0.92 inches, so that means we got 0.92 inches. And I'm going to give that a subscript M. That means inches measured on the map. And that is going to be equivalent to 1,200 inches, subscript R, measured in the real world. And there is our ratio. But that's kind of cumbersome to work with. So when we have map scales, we like to set that up as 1 unit in the real world is equivalent to some number of those same units 1 unit on the map is equivalent to some number of those same units measured in the real world. So what we want to do is set this up as a ratio of 1 over x, and then we can simply cross multiply. And that's going to be, in this case, 1 inch measured on the map is going to be some number of inches in the real world. This will be our ratio. It doesn't matter what units we're doing, we just want to keep them the same units, and we're going to standardize for this example in inches. So now when we cross multiply and solve for x, we're going to get 1200 divided by 9.92, and we solve for x, and x equals 1,304 inches in the real world. So there is x. That means that our scale is 1 to 1,304. So there is our horizontal scale, 1 to 1,304. That means 1 unit measured on the map is equivalent to 1,304 of those same units measured in the real world. So we just experimentally determined the numeric scale of this topographic map. And remember, if you take any image of a map that has a numeric scale on it, and if you distort that image at all, if you reproduce it, you distort it, you project it, you are changing that numeric scale. The scale bar, however, changes with the distortion, so you can always use that scale bar to figure out what the numeric scale is. But we need to figure out the numeric scale because we need to figure out how we're going to scale our vertical scale on our cross-section. So for this example now, we're going to do a 2 times vertical exaggeration. Why do we do that? When we vertically exaggerate the cross-section, it brings out the topography. We can see it better. Because the real reason is most topography, if you just make a topographic profile, it's going to look almost flat. It's not going to look very impressive, which is the way it really is. But if we exaggerate it, we can bring out that topography better. We can see changes in slope angles, changes, inflection points, and so forth. But realize that as soon as you exaggerate it, you can't simply put up your protractor and measure a slope angle because you're exaggerating slope angles. Similarly, if it's a structural cross-section, if you vertically exaggerate, the dip angles are going to be exaggerated. The apparent dip angles are going to be exaggerated in that cross-section. So you have to be really careful about vertical exaggeration and what you use it for. And the other thing you need to do is figure out what can you fit into that space of your cross-section. How much do you want to vertically exaggerate it? And the way you want to do that is look at the space you have and then look at the total amount of relief that you have on your map. In this case, we have, if we go a little bit, if we go up to 520 and down to 460, our total relief is 60 feet. So our total relief is 60 feet. Total relief, it's actually a little bit less than that. But we'll call it 60 feet because that gives us some room to work in. And now we want to figure out, is a 2-time vertical exaggeration going to work in the space that we have? In class, the other day we did an example. We tried 10-foot vertical exaggeration of the same map, and we found that that's not going to give us, we don't have enough space to do that cross-section. But if we do a 2-time vertical exaggeration with a relief of 60 feet, we're going to see how that works. So now we need to figure out, okay, what's our scale going to be at 2 times vertical exaggeration? So we're going to take this ratio of 1 over 1,304. There's our 1 unit measured on the map is equal to 1,304 of those same units in the real world. And we're simply going to multiply that by 2, which is, of course, 2 over 1,304. And we can simplify that into 1 over 652. So there is our vertical scale. In other words, it's 1:652. Now we need to figure out, is that going to work for us? So if we take 60 feet I'm going to put subscript R for the real world. That's our maximum relief of this map. We said that here, 60 feet. We want to convert that into inches measured on the map for our vertical scale. So that means that we have we're going to have to convert those feet into inches, right? So 60 feet times 12 inches per foot is 720. So we have 720 inches in the real world, and we have to figure out if that's going to fit at this scale. So let's say 720 inches in the real world, and our vertical scale is 652 inches in the real world for every inch measured on the map. So then we take 720 divided by 652, and I get 1.1 inches. So that means I've got plenty of space to do this down here at 2 times vertical exaggeration. So that was just my test. Notice if we had done 10 times vertical exaggeration, it's going to be 10 times. So in other words, it's going to be over 10 inches in the space here. And that wouldn't work for us. We simply don't have space. I mean, we could do it on a separate piece of paper, but in the space we have beneath this map, it's not going to work very well for us. So now we know that a 2 times vertical exaggeration is going to work for us. And we're going to create a vertical scale that is in increments of 10 feet. So now we need to figure out, okay, if we divide it into an increment of 10 feet, that would be 10 feet measured in the real world, and we need to figure out what that is in inches on the map, right? Well, again, we're going to have to convert those 10 feet into inches. So 10 feet times 12 inches per foot equals 120 inches in the real world, right? So we have 120 inches in the real world, 120 inches in the real world, and we use our vertical scale of 1 over 652. That means we're going to have 1 inch on the map. Sorry, that should be an IN on the map, is equal to 652 inches in the real world. We put that in the denominator. Running out of space here. Move that a little closer. Sorry about that. That means every 10 feet is going to be equal to 0.184 inches. So there we go on the map. Every 10 feet is 0.184 inches on the map. That's at 2 times vertical exaggeration. Remember, our vertical scale here is 1 to 652, which is half of 1304, of course. All right, so now we're ready to make our cross-section. So I've already done this. You're going to have to do the same. I just saved myself a little bit of time for the video to make the video a little bit shorter. So what I've done here is I've projected all of my lines perpendicular to the trace of our cross-section A to A prime. And so I first projected down the limits of the cross-section. So there are the limits of it on the east and west edges, A to A prime here. And then we're going to have our vertical scale here. The horizontal scale stays the same. Horizontal scale is still 1 to 1304, but now the vertical scale is 1 to 652. So remember, I calculated down here that every 10 feet is equal to 0.184 inches, and I measured off already each one of those increments. So each one of these 10-foot intervals here is 0.184 inches. So I took that number 0.184, multiplied it by 2, multiplied it by 3, multiplied it by 4, and simply added all those up. And then I transferred those same tick marks over to the west side of it and made my scale there. So once I did that, then I could simply draw my horizontal lines here of equal elevation there for reference. And you want to draw those fairly lightly. Then I came back in and I projected a line perpendicular to the line of our profile, projected that down into our cross-section, our profile view, perpendicular. Every line projected from the point where a topographic contour line crosses the line of our profile. So I've got one coming down here. That's going to be a line of 470 feet elevation, and another one coming down here at 470, 480, 490, and so forth and so on. And I want to project those down to the elevation on my cross-section. So let's do this one. This one comes from 470, and we bring it down here. That means there's our elevation to 470. This one is also at 470 because we've got a little valley here. It goes a little bit downhill, and then it comes uphill on the other side. 480 projects to here. 490 projects to here. There's 490. 500 projects to here. Sometimes it's useful to label these lines of projection, or you can simply keep track of it. And then up to 510. On the other side of the hill, we've got 510 projecting to here, 500 projecting to here, 490, 480, and 470. So there is my cross-section projected down. Now all I need to do is use a little bit of geomorphic common sense, and I know that it never gets down to 460 on this side, but it comes below 470, so I'm going to give it a nice smooth curve for my hill slope. And then it crests out a little bit above 510. We're not quite sure how high, but let's just give it a nice even curve there. Not quite to 520. And then down the other side by connecting our dots. And here's our little stream valley down here, where it's going to dip down. We're going to have a stream in there, and it comes back up to a slightly higher elevation on the other side. So there is my topographic profile. And that is it. We've just done it. So the big key here is to figure out what your vertical scale is and what increments we do. Notice if we had not vertically exaggerated this, all of that topography, we could have easily done that, by the way, but all of that topography would be in half of that vertical distance. So that would have squashed this down. It just wouldn't look quite as impressive. So sometimes it's really visually appealing to vertically exaggerate that. But remember, as soon as we do that, it changes the apparent slope angles here or any angles of dipping layers underneath. And so you can't simply take a protractor and measure that up. The other point I want to make is the reason I really love these Westcott ruler protractors is because it makes it really easy to project perpendicular lines and to measure increments of that. We've got tenths of an inch scale measured on one side and centimeters on the other, so lots of different options. And of course it has a protractor that we use for other things. So I hope this video helps.